Hello, let's talk about the beta decay of bismuth-210. So during a beta decay, a bismuth-210 nucleus splits itself into a polonium-210 and a beta particle. The energy released provides for the Ke of the daughter nucleus and the beta particle. Since the total momentum must be zero before and after the decay, we know that the polonium-210 and the beta particle must have equal but opposite momentum. And if we write Ke as p squared over 2m, and since we already know the daughter nucleus and the beta particle have the same momentum, we know that the two of them will have Ke according to the inverse ratio of the masses. But the beta particle's mass is about 1U divided by 1800, whereas the mass of the polonium is 210U. So this ratio will work out to be practically zero, which means the Ke of the polonium is practically zero. Now, given all these people's masses, we can calculate the energy released by taking the initial mass minus the total final mass times c squared. So I've done this calculation for you. The energy released during the beta decay of bismuth-210 is 1.16 mega electron volts. Since the polonium-210 gets practically nothing, the Ke of the beta particle should be 1.16 mega electron volt. So if we measure the Ke of the beta particle, we expect to get 1.16 mega electron volts. So if we were to draw on a chart a histogram of the energy distribution of the beta particles, we expect each and every beta particle to have the energy of 1.16 mega electron volt, isn't it? So it was a big surprise to everyone when it turns out that the beta particles seems to have a distribution of Ke. It's a surprise because we expect the bismuth-210 to always spit out a beta particle that has this amount of energy. The energy should not change from one decay to another. So let's look at the math again and see whether we made any mistake anywhere. There cannot be anything wrong with this line, right? Because PCOM is true all the time. These lines also look solid. The mass of the beta particle and the mass of the polonium-210 is fixed, right? It doesn't change from one decay to another. Similarly, the energy released during every decay of bismuth-210 should be fixed because all these masses are fixed numbers. So nothing in these calculations should change from one decay to another. And so all beta particles emitted by the beta decay of bismuth-210 should be 1.16 mega electron volt. So why is there a distribution? Let me give you an analogy. Suppose your father has two children, yeah? That's you and that's your sibling. And your father announces that he'll give out a total of $100 to his children every month. Besides that, he will also make sure that you and your sibling will be given the same amount of money. So how much do you expect to get every month? $50, $50, right? Every month you should get $50, $50. But it turns out some months you'll get $50 each. Some months you'll get $1 each. Some months you'll get $5 each. So you ask your father, hey, you're not following your own rules, man. But your father say, no, I am following these two rules all the time. So what does that tell you? Your father must have a third child. So when the third child gets $50, the two of you will get $25 each. When the third child gets $98, the two of you will get $1 each. So same here. We used to assume that during the beta decay of bismuth-210, the beta particle is the only particle that's emitted. Because you have only two particles, for the total momentum to be zero, there's only one possible outcome for these two particles' momentum. And therefore, there's only one way for these two particles to share the energy released during the beta decay. Now, what if the bismuth-210 spits out another particle besides the beta particle? So if you have three particles, then there are infinite number of ways for these three particles to have momentum that sum up to zero. And therefore, there are infinite number of ways for these three particles to share the energy released during the beta decay. And that can explain why the bismuth-210 can emit beta particles with a range of energy. It turns out that this third body, if it exists, must have a very, 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 very small mass and also carries no charge and therefore practically doesn't interact with any matter, which is the exact reason why nobody suspected that it existed, right? So it took the scientists many, many years, but eventually this particle was detected and they came to be known as neutrinos and antineutrinos. Now, as far as the A-level syllabus is concerned, you don't have to know about the beta positive decay. And you don't even have to name this particle as the antineutrino. All that's required of you is to appreciate why a distribution in the Ke of the beta particles informs us that there's a third product in the beta decay. Alright, that's all. Ta-ta!